Now let's come to Jacobian. Jacobian actually is a mathematical term. We use it in robotics also, but it's actually a mathematical term for the functions which are actually for different functions which are actually themselves a function of different variables. So let's assume we have some functions like y1, y2 up to yn, which is function of itself, a different function of variables. Let's say x1, x2, x3 up to xn. Now this whole can be written in a compact form as y is equal to f of x, correct? So now, as we see from the definition, Jacobian is actually the matrix of partial derivatives. So we can always find out the change in y1 with respect to all these variables. So that can be represented like this: partial derivative with respect to all these variables of the function f1, and similarly delta y2 and up to delta yn. Now this can also be put in compact form, something like this: delta y is equal to dou f by dou x to delta x. Now this all can be represented in the form of a Jacobian matrix. So this is the Jacobian function, which is nothing but this one, and which is nothing but the matrix of partial derivatives. All these are actually components of the Jacobian. Now this type of relation is very useful because when we have in robotics, we have, let's say, the end effector coordinates, which could be these, and we have the joint coordinates. Alright, so we can also find out a relation between the end effector coordinates and the joint coordinates, and but particularly this is very useful at the velocity level. So in robotics, Jacobian actually gives us the time varying linear transformation between the end effector velocities and the joint velocities. So we have seen with kinematics or forward kinematics, we get a relation with end effector position and orientation as a function of the joint coordinates. So let's say capital X here denotes the vector of end effector, let's say position and orientation, and small q actually defines the generalized coordinates, or you can say the coordinates of the, or you can say the joint coordinates. If we differentiate this, we should get something like this: x dot is equal to jq q dot, as per the definition of the Jacobian we have seen in the previous slide. Now to find out this j, which is very significant actually, we can make use of this homogeneous transformation matrix, where we have the information of rotation matrix and the position of the end effector. So if we look at this type of matrix, so we have P E, which actually represents the coordinates of the end effector with respect to base, because that's what the homogeneous transformation matrix for us in a general sense would actually mean. And REQ actually is a rotation matrix which defines for us the vectors, the unit vectors as represented, or you can say the unit vectors of the end effector as represented in the base frame. So if we see that this rotation matrix and this position vector actually both contain the information about the end effector position and orientation with respect to the joint coordinates, this is enough for us actually to derive the Jacobian. So this is how we do it. So we can simply differentiate the end effector coordinate, that is P dot, and try to segregate it in the form of joint coordinates. The rate of joint coordinates will be left out with JP, which will be equal to the Jacobian matrix. But this is just for the positional coordinates, or you can say the Cartesian x, y, and z motion. The other part of the Jacobian, that is the orientation, actually will be mapped like this: omega e is equal to j, you can say j o, with o means orientation, and q dot. So this can be then together put like this, where we see ve here refers to the both linear and angular velocities of the end effector actually, and q dot defines the joint velocities. So we had defined the end effector velocities mapped to joint velocities by the matrix JQ, where JQ is actually JP and JO stacked together. So this is our Jacobian. This Jacobian is actually very useful. We'll see it in the coming slides. So one way to do it is just simply differentiate this PE dot and get to have this JP. But if we see RE actually is a matrix. So getting an RE dot actually will not give us just the three angular directions or the angular velocities. So there are, so that's what. So if we just differentiate this and get 3 3 3, which is the whole matrix, we will actually get something like I will just maybe do it here. So if we see PE structure generally or RE structure, RE is generally, or you can say RE here would mean any rotation matrix. So it's like something like you can say R11, R21, R22, R31, R32, R33. If it's something like this, and PE is equal to just let's say XE, YE, and ZE. Now, doing the differentiation of this would give us extra E dot, YE dot, and ZE dot. Right. We'll get this is equal to some Jacobian matrix. Okay, JP here is a function of joint joint velocities q1 dot, q2 dot up to qn dot, for example. So this is okay, there is no problem. But when we see RE, so if we do RE dot, so we will have something like R11 dot, R21 dot, something like this. So it will again be so we'll have again 1 vector, 2 vector, and 3 vector. So we have 3 cross 1. So this JP is actually equal to 3 cross n because we have Q which is equal to n cross 1. Alright, some more terms. So this will also be our Jacobian in this case, but this will be having some dependent terms. So that's why we leave it in this case here. You can maybe refer to the books for more definition of this. So this is what we generally call a geometric Jacobian, and this is almost similar to the actual Jacobian that we require, but there are some dependent terms. So that's why we would generally skip this type of way of obtaining the Jacobian. Rather, we have a very simpler way of obtaining Jacobian by just looking at the velocity, the linear and the angular velocity of the end effector, and just you can say deriving Jacobian out of that only. So in the next slide we'll see for a tooling plane round, initially for a simpler case, we get this T matrix that we have seen already how to get this with the DH parameters. So this is the rotation matrix of this tooling arm, and this is the PE vector. So in the tooling arm, so we know that the end effector can just make an object move along x and y direction. So it has only two linear velocities. So that is, it can have you can say x dot and y dot. So x dot and y dot. I'll just skip this. Alright, so now we know that P is here, this and this and this. So x, y, and z coordinate is 0 because it's a planar manipulator. So we can easily find out the differentiation of these two terms, which will come out to be something like this. A1 cos of 1 is minus of sine 1 plus A2 cos means sine of 1 2 Because of 1 2 we'll have theta 1 dot theta 2 dot, so we'll have theta 2 dot, we'll have another component, so this will get out to be like this. So we'll get a 2 by 2 matrix. If you want, we can do just the analysis here. So if we just take px a1 cos 1 plus a2 cos 1 2, now as per the definition of Jacobian, we have to do the partial derivation of this with respect to theta 1 and theta 2. So we'll get minus a1 sine 1 theta 1 dot minus a2 sine 1 2 theta 1 dot plus theta 2 dot. Okay, and py is equal to a1 cos 1 plus, this is px dot, so py dot is equal to a1 cos 1 plus or theta 1 dot plus a2 cos 1 2 theta 1 dot plus theta 2 dot. Right, so if we arrange this, px dot py dot is equal to minus a1 sine 1, if we take theta 1's first, minus a2 sine 1 2, and because theta 2 it's like this, we will say a2 sine 1 2 minus here a1 cos 1 plus a2 cos 1 2, and for here we have another component with theta 1 2 theta 2 dot, so it's like a2 cos 1 2, this is theta 1 dot theta 2 dot. I hope you are able to actually correlate this. So now we can say px dot py dot is equal to j theta 1 dot theta 2 dot. So we have got the relation between end effective velocities and the joint velocities. That is why Jacobian, and Jacobian here is this or this. Right. Similarly, we have for 3-link planar arm, so we can easily find out its transformation matrix. But in this case, you will see that it's not 2-link, it's 3-link. So it means it can actually have 2 linear velocities and 1 rotational velocity. So because of that, it will have 3 components of the Jacobian. It will be 3 by 3. So it will be obviously differentiation of this px py. Orientation in this case is simpler because we know that theta phi will be equal to theta 1 plus theta 2 plus theta 3, and phi dot will be equal to theta 1 dot plus theta 2 dot plus theta 3 dot. So the orientation of this will be actually equal to sum of the rate of change of these. And this can also be found from a different way also. Now we have anthropomorphic arm. For this, the transformation, homogeneous transformation matrix looks like this, and then accordingly we have the Jacobian by simply differentiation of all these. So this can make an object actually place an object in x and y and z direction only, no rotations possible. So because of which it will have 3 linear velocities, px dot py dot pz dot, which will be mapped to theta 1 here, theta 2 here, and theta 3 here with this Jacobian matrix, which can be easily found by differentiation of these 3 components. So it has px, py, and pz also. So you can simply differentiate them and get these. Now we can also do computation of Jacobian by propagation, the velocities that we saw in the link velocity propagations. So if we do that way also, we have simpler ways of computing Jacobians. So we do calculate, we do calculate omega there as omega I plus 1, as we have seen earlier, is equal to omega I of I. Okay, with some rotation matrix of I into I plus 1, isn't it? So we have seen, and then it is also equal to omega I plus 1 with respect to I in I plus 1 in this case. So this type of basically can actually give us finally, because this is about I. Similarly, this will give us omega of E in E, which is end effector. Similarly, we can get V in E. So accordingly, we can use those and then open up those to get something. I can say, and then actually put it this way to get the Jacobian. So where we have simpler E1, E1 cross A1 E, E2, E2 cross A2 E, and similarly up to En and En cross AN E. So it's very important to know that if there is a difference between joint being prismatic and revolute, so you can directly from a configuration of a robot actually find out if the joint is revolute, then this type of thing holds true. But if the joint is prismatic, then in that case this part will go to 0 and this part will go to just the E, which is where E denotes actually the vector of, or you can say E denotes the axis of the joint, which is the Z axis in our case. So you can say Z1 or Z1 cross A1 E and all those things. So this is not this comes from here actually. You have seen omega actually is nothing but theta 1 dot Z1, or we can also write that as theta 1 dot E1. So those E1s and theta 1s goes here dots and E1s comes here. Similarly, all this procedure, this is one of the very good procedures, but we'll just keep it to you. You can just read it from the books or from some other lectures. You can find out this is a very good way of actually finding out the Jacobian when it becomes difficult to do it with, or maybe let's say it's difficult to do it with just the rotation matrix. So this one makes it a little easier to do it. Now let's look at the kinematic singularities. Now we are actually coming to a place where we know that, let's say we have now the joint velocities, and we have been able to find out the mapping between the end effective velocities and the joint velocities. Now, is it possible to attain the joint velocity every time for a particular end effective velocity? We'll see this. So there's a small mistake. So we know that x dot is equal to j of theta dot. So theta dot actually equals to j inverse x dot. So here it has to be x dot. Alright, so you can say that for any particular end effective velocity, what are the corresponding joint velocities. But if you see from this mathematical expression, it means that Jacobian inverse is involved, which means that Jacobian has to be invertible. So the matrix has to be invertible. So if Jacobian is invertible, then only we have finite values of the joint velocities for a given end effective velocities. Now, but what happens is Jacobian becomes singular. You can say this matrix loses rank. There are some similar columns, similar rows. So the matrix, Jacobian matrix, actually loses rank, which means that the inversion is not possible. So that those places are known as singular locations. So in those places, actually, the manipulator loses a certain degrees of freedom as we from the Cartesian space. So since Jacobian is composed is nothing but it's a function of the thetas, which means it's function of the configuration of the robot. So it's very important, for designing robots. While we design robots, actually, we need to be very careful that we don't actually operate in the singular regions. Now, singularity is of two types. We have workspace boundary singularity. So let's look at the two link manipulator. This is link 1, this is link 2. So if we stretch them completely like this, so if you see that we cannot go now at this location, if we ask a robot to go here, which is not, this will not be possible. So if you see that to achieve some velocity in this direction now, it will not be possible. So the robot actually, since the robot was doing this thing, let's say somewhere here inside, the robot can go here, the robot can achieve some velocity here, some velocity here, but now at this position in the same plane, the robot is not able to achieve any velocity here because of stretching of this, which makes it what actually we call as singular. So this is known as the workspace boundary. This is the stretch maximum. Now if theta 1 actually changes, so this can go like this, but if the angle between this and this, which is actually theta 2, is 0, then this achieves something called as workspace boundary singularity. At this point, actually, the manipulator cannot actually move in this direction, though it was possible for the manipulator to go in this direction at, let's say, this point inside the workspace. Similarly, when this angle goes to pi, which is 180 degrees, something like this. So let's say this link has come here now. Now this thing also makes it singular, because this robot cannot move in this direction. It cannot achieve any velocity in this direction. So this also becomes a workspace, because theta 1 again can change, but it cannot go beyond this point. So it cannot achieve any velocity beyond this point. This is also this singular region. We call this as workspace boundary singularity. Now this can be easily visualized for tooling manipulator with a Jacobian. So this is the Jacobian of tooling manipulator. This is we can also look at there are two Jacobians that have been put up. So one is putting up it this way, where you have the Jacobian, and then you basically find out its determinant, and it comes out to be like this. For theta 2 is equal to 0 and 5. So this actually loses its rank. So let me just check for the Jacobian in the base frame. Yeah, so for this one we can have the actual Jacobian to be like this, which is in base frame. Jacobians also can be put up in different frames. So the actual Jacobian would look like this, or you can say Jacobian in base frame. So similar to what we just derived previous slide. L1 के बजाय can have A1, A2 and all those things. Alright, so again, if we take the find out the determinant of this and put theta is equal to 0 and 5, you will see that the Jacobian actually, or you can see if you put Jacobian to be 0, so you will see that we'll get theta 2 equal to 0 and 5. Okay, so that can be, so this and this will lead to have same result. So this is actually Jacobian in frame, you can see frame in frame 2. You just leave this part initially. This one can make you grasp this easily. So if you see this structure is similar to, I'll just go back. So exactly similar to the two link Jacobian, this one. All right. Let me go to singularity type 2, where we have workspace interior singularities. So we have, suppose, a 3-link manipulator. So there could be a case where these two links actually come together or be in line. So in this case also this becomes singular, but this is not the workspace boundary singularity, because this can further move inside by rotation of this thing. It is possible to move inside, but because these two are aligned together, so at this point the manipulator cannot actually achieve a velocity in this direction. So this is again a singularity, but this is inside, or you can workspace interior singularity. And it can also happen in this case where these two links are like this and the third link goes like this. These two are in line, only two links are all in line. This becomes also singular point. Right? So this can also be analyzed by Jacobian and then putting that to 0, find out its values of the angles at which this thing happens. So this is evident that this happens at theta 3 equal to 0 and pi. And this can also happen where these two are at an angle other than 0 and pi, but these two may get inline, something like this. Let's say this goes inline and there is another like this. This could be also a possibility.